Hello everybody. In this lecture I will be discussing with you about the operation of bias transistor and mechanism of amplification by the transistor. In normal operation, I have already told you that the base emitter junction is forward biased and the collector base junction is reverse biased. So let us see with this sort of biasing how the bias transistor will work to provide us amplification of signals. Now let us look at this circuit. You can see it is the NPN biased transistor with a load connected with it, RL. In this diagram you can see the voltage source VEE is connected in such a way, since the BJT is NPN, that is NPN, so this side is N, that N is connected with negative terminal of battery and P is connected with positive terminal, so VEE source is making the base emitter junction forward bias. Similarly, N, the collector is N, that N is connected with positive terminal of VCC, that means the source VCC biases the collector base junction in reverse direction. So this circuit shows the it is normal way of biasing, and the reference current and voltage directions and polarities are respectively shown in this diagram. So let us come back to these two diagrams to see how the operation of bias transistor is happening for amplification of signals. Now in this case, one thing has been assumed, that the resistances of bulk of emitter, base and collector regions are negligible and the applied voltage are appearing entirely across the junctions. Now the forward biasing of the emitter base junction will permit a large number of electrons to be injected from the emitter side into the base side, and as because of high doping of emitter, the conductivity of emitter is much larger than that of base, because very small number of holes, and because of that very small number of holes, because of light doping and low conductivity of base regions, very small number of holes will be flowing from the base into the emitter side. So in majorly the majority carriers electrons at the emitter side, because of its high doping and high conductivity area of the emitter region, the electrons as the majority carriers will move much into the base side than the holes that will that is the majority carrier in the base area will move towards the emitter side. So the emitter current will be almost entirely due to the flow of electrons only in an NPN transistor. Now these electrons, after entering the base region, will produce a concentration gradient, and that concentration gradient will be larger at the emitter junction than at the collector junction. So therefore, from the emitter side to the collector side, principally by the method of diffusion technique, the majority carriers as electrons will move. Now let us look at these two diagrams, how this is being happened. This is the emitter injecting free electrons into the base, this diagram, and this diagram is free electrons from the base flow into the collector. So this diagram primarily giving us this diagram, emitter to base movement of electrons, and this is base to collector movement of electrons. So when the base emitter junction is forward biased, immediately the electrons from the emitter will not move into the base till the time the base emitter diode is getting from VBB a higher potential than VBE, because VBE we know is for a silicon diode 0.7 volt. So once the base emitter junction is forward biased, it requires at least 0.7 volt to be supplied from VBB to this VBE, so that the base emitter junction is actually forward biased and the carriers will start to flow the electrons. So once the VBB is greater than the 0.7 volt, that is the barrier potential, the emitter electrons will enter the base region from the emitter region. Now once they have entered, now let us see, once they have entered from the emitter region due to this forward bias of base emitter junction from emitter region into the base region, once the emitter electrons are injected and they are now at the base region, they will get to flow to two different directions, one towards the collector and another through this terminal of base where the RB base resistance is connected, because at the collector side it is connected with positive terminal of battery, and at the base side it is also connected to the positive terminal of the battery of the two sources VBB and VCC. So for either of the cases, electrons will get attracted towards the positive electrode of the batteries of the sources VBB and VCC. So at the base region, the injected electrons from the emitter as majority carriers will be having two options of moving towards either collector or towards the base or go out through the base terminal. So let us see which direction will be the predominant passage of electrons in this case. Now most of the electrons will be seen to be continuing its journey towards the collector side but not towards the base side. This is because of two reasons. First, the base is lightly doped and it is very thin. Because of very thin area of the base, electrons will be required to stay in the base area for a less amount of time. So there will be less amount of time required for the electrons to be injected from the emitter side to cross over the base area to go into the collector side immediately, because the area of crossing the base is very less, so it will require very less amount of time. So not much amount of time for the electrons will be having or will be required to remain at the base area. So because of that, they will immediately move into the collector area. So very thin area of the base will be helping the electrons to move more towards the collector area than to go out through the base terminal area towards the left side. So this is one reason. The another reason is that since the base is lightly doped, that means base is doped with majority carriers as holes, so the number of holes, the concentration of holes will not be that much more higher as compared to the injected electrons from the emitter to the base area. That and because of that, there will be some, although there will be some recombinations, but that recombination will not exist in a very high amount or in a very high percentage. The chances of recombination, although will be there at the base area between the electrons and holes existing in the base area as the majority carriers, but still because of light doping, the chances of recombination, although being there somewhat, but still the recombination will not take place that much more high because of low doping or lightly doping of the base area with the majority carriers of holes. So as a result of that, the lifetime of electrons passing through the injected electrons from the emitter side passing through the base area will be much higher, and for them the chances of recombination will be very less. So more and more number of electrons will go will move inside the collector region easily without being recombined by the holes at the base area. But since there will be some amount of recombination with the holes, so only a few free electrons will recombine with those holes in the lightly doped base area, and they will become valence electron from free electron after getting recombined with the holes, and they will flow through the base resistor RB to go inside the and to be gone inside the VBB supply because being attracted with the positive electrode of VBB. So this current will be called recombination current, or it is the loss current, recombination current. So that means the recombination current is produced from the emitter current. So recombination current is a part of emitter current. Emitter current was produced primarily by the injected mobile electrons from emitter into the base. So recombination current will be a part of the emitter current, because recombination current will be produced by some of the electrons to be recombined with the majority carrier holes at the base region, and that part of the recombination current will be subtracted from the total emitter current, so that the remaining current will be called the collector current. That means they will be constituted with the free electrons that remain, overcoming the process of recombination at the base area, to be forwarded towards the collector region. So the collector current will be emitter current, total emitter current, minus the recombination current or loss. Recombination means it is the lossy current produced in the base area to give the resultant collector current. That means the electrons, those are being collected by the collector, overcoming the recombination process at the base area from the total part of emitter injected electrons from the emitter area. So this is the way how the transistor will work. And now all the collector or major number of free electrons will be collected by the collector, and they will naturally face the attraction of positive electrode of the source VCC, and they will be moved into this collector moved into this path through the collector resistance to go inside the VCC source. So this magnitude of collector current is hence will be little less than the emitter current, but very close to the value of emitter current, because few electrons are lost by the process of recombination out of the emitter current in the base area, and they will move out from the base area through this RB. So whatever emitter injected electrons resulting the emitter current will be forced into the base area, very small portion out of it will be recombined with the holes in the base area, and they will move out through this base area RB to go into the VBB, but major number of free electrons will escape from the process of recombination to go from the base area into the collector region, and they will be naturally attracted to go into the positive electrode of the VCC, source VCC, and they will constitute the collector current. So collector current will be almost equal to the emitter current, and the difference of the emitter and collector current will be the recombination current, which will be called base current. So the collector current denoted by IC, emitter current denoted by IE, and the recombination current is the base current, which I have already told you in the last lecture, it is called IB. So we can say the IE is nothing but the sum of IC and IB. So the whole emitter, this is the current injected by the emitter into the base area. Base current is made by the recombination process, and that is being lost through the base area, and the remaining free electrons, those are collected by the collector, will constitute the collector current to go into the VCC source. So almost all the free electrons that will go into the collector will, once again, they are in the collector, they feel the attraction, and they will go inside the VCC source. So because of this, the free electrons will flow through the through RC, this resistance, to be collected by the positive terminal of the subcollector supply voltage. So if we summarize the whole process, what we can say in a few lines, that the VBB forward biases the emitter diode, forcing the free electron in the emitter to enter the base. The thin and lightly doped base region gives almost all these electrons enough time to diffuse into the collector. Some of the electrons will be lost by the process of recombination to go out through the base terminal into the positive electrode of VBB, which will constitute the base current, but the major number of electrons will be passed on to the collector area, will constitute the collector current, and they will eventually escape through this collector resistance RC to be collected by the positive terminal of source voltage VCC. So this is the way of operation of bias transistor and the mechanism of amplification by the transistor. We can say the emitter based junction is forward biased, which will mean that the dynamic resistance of the junction is small, and collector based junction being reverse biased, the dynamic resistance for a reverse bias junction, you know, it is dynamic resistance means it is the change in voltage, ratio of change in voltage with change in current. For a reverse bias junction, the dynamic resistance is large, so we can say that the junction resistance around the emitter base area is small and the junction resistance at the collector base area is large. So that means the two junction area is having two different resistances. So we can say that the transistor action is happening, actually a current is passing from a low resistance input circuit to a high resistance output circuit, resulting in power gain. That means the electrons are moved from a low resistance area into the high resistance area. So we can say the resistance being transferred from one junction area of low value to another junction area of high value. This transfer of resistance is called, so transfer of resistance is happening from low resistance junction area, low value at EB junction, that is emitter base junction, to high value of CB junction, that is collector base junction. So in this way we can say the resistance is being transferred from one junction area to other. So this is called transferred resistance. This is called transfer of resistance or transferred resistance. And from this concept of transfer of resistance, the name transistor has come. This term tran comes from transferred and zistor comes from resistor. Resistance is the property of resistor, so transferred resistor means transistor. So from here this transistor name has come because of transfer of resistance from one junction area of low value to another junction area of high value, because of forward and reverse bias at the low and the high junction area, high resistance junction area respectively. So this is this is all about the mechanism of amplification of transistor and operation of bias transistor. Now let us see the gain of the amplifier. Gain of the amplifier. Now already we have seen that the mechanism of amplification by the transistor, how this has been happening in terms of the transfer of electrons from emitter to ultimately to be collected by the collector area. Now when let us see how the term gain that has been conceptualized from this theory. When an AC voltage is superimposed on the DC voltage VEE, suppose at the input, VEE that is being applied at the input, a voltage source, in that case there will be a periodic variation of emitter current, which in turn will give rise to similar periodic variation of collector current, because once the alternating signal for amplification purpose is being applied at the input of the BJT, that will make the input signal to be varying, which will eventually result the output signal, that is at the collector current, that will also be varied. So the magnitude of this alternating component of collector current will be almost equal to that of the corresponding component of the emitter current. We have just seen a little while earlier, because we have seen that the emitter current is almost equal to collector current, only there is a part of base current which is being lost because of recombination. Base current is nothing but the lossy current or the recombination current produced by the transistor. So this alternating component of the collector current will develop an alternating voltage drop across the load resistance RL, because a load resistance is connected over here at the output side. So it will produce a voltage drop, the collector current or the output current. So this forms the output voltage of the transistor amplifier. So if this collector current IC is passed through this load resistance RL, a voltage drop as per the Ohm's law will be observed, denoted by VO here, and this is nothing but the output voltage of the transistor amplifier. This is the amplified form of voltage at the output of the transistor amplifier. If the AC component of the emitter current is denoted by IE, AC component is always denoted by small notations, small variable value and small subscript value. So emitter current is AC component of emitter current is IE. This is AC component of emitter current. That means which we have previously called as capital IE. Capital IE is the DC notation and small IE is the AC notation. Capital means DC and small means AC in analog electronics conventional notation. Please remember this one. Then the input signal voltage Vin is given by Vin, if it is the input signal voltage, input signal voltage, then it is given by IE, AC component IE into Rin, where Rin is the input resistance of the transistor circuit as per Ohm's law. And this input resistance is nothing but the dynamic resistance of the emitter base junction. This is nothing but the dynamic resistance, dynamic R, this input resistance. So dynamic resistance of the emitter base junction multiplied by the AC component of emitter current will give you the input signal Vin. If now IC be the AC component of collector current IC, if this is AC component of collector current IC, then and VO is the alternating output voltage across RL. We have already seen that VO is output voltage across load, then we can write VO equal to minus IC into RL as per Ohm's law. The negative sign indicates an increase in the collector current, makes the bottom end of the, because you can see from the diagram that IC is shown convention as per convention to be flowing from collector terminal into the transistor, but the direction of VO, polarity of VO, output voltage, is shown upper side with plus sign and lower side with minus sign. So that is as per the opposite convention of the flow of current IC. So that's why this negative sign is being used. So the voltage gain AV of the transistor amplifier is defined as, now if AV is the voltage gain for the transistor amplifier, it is defined as the ratio of alternating component of output voltage to the input voltage. It is nothing but VO by Vin. So AV is given by minus ICRL divided by IE Rin, just ratio of the two, output voltage by input voltage, that is the voltage gain. Now the quantity from here, the quantity minus IC by IE, this quantity is referred to as current gain, denoted by AI. This is current gain. So inside the voltage gain there is a part of current gain which is minus IC by IE, and you can easily understand from the previous circuit diagram that the direction of flowing of IC, that is the collector current, and emitter current, that is opposite, and so the negative sign is justified here. The signs of IC and IE the signs of IC and IE are opposite, and if we consider for them it is same. So suppose if we just revert the direction of either IC or IE, then this negative sign will be abolished, and in that case the AI will be of a positive value. and if AI is positive value, that means this sign will not be there, so voltage gain AV will also be positive if we consider the IC and IE to be in the same direction for the sake of simplicity, or rather if we take the mod of the value. Now once again refer to the previous circuit diagram, we have shown a little while earlier. This circuit diagram, you can see IE and IE are oppositely directed, so that's why that negative sign is being justified. And because of IC that is being flown from as per this direction, it is flown from bottom to top through this RL. So actually the VO should be having polarity plus at the bottom, minus at the top. So because of its general convention, plus is taken above and minus at the bottom, that means that negative sign is justified because of this minus ICRL. VO equal to minus ICRL, that negative sign is justified. So now an increase, so if we now refer to this figure, an increase in V input voltage applied to the input terminal between base and emitter reduces the forward bias at the emitter base junction. Now if we increase the Vin, because you can see that the minus is connected to this side and plus is connected to this side. So if we add another voltage source, suppose like this, plus and minus, and if it is go on increasing, an alternating signal, if it is go on increasing, this source, this value VE will be subtracted from this alternating signal value. So as this alternating source will go on increasing, that means the overall voltage at the input circuit of the transistor will be reducing the forward bias at the emitter base junction. This will result in the decrease of collector current, because as the forward bias is decreased, that means output will also decrease, so collector current will also be decreased, making the top end of RL more positive. That means this value of IC will become down, will become lesser. So if this will become lesser, that means the IC is flowing through this direction, so this side will be naturally positive and this side will be negative. Now if this value is coming down, so the bottom side will be less positive and upper side will be more positive. So the top end of the RL will be more positive with respect to the bottom end. So an increase in Vin thereby causing an increase in VO. So we can say that if this Vin is increased at the input circuit of this transistor, this VO, this upper side of VO will be more positive than the lower side of VO, because IC will be decreased in that case because of forward bias being decreased at the overall forward bias being decreased at the input side. So because of IC being decreased, the lower terminal of RL will be less positive than the upper terminal. So we can say that as Vin go on increasing, VO should go on increasing. In this case, there is no phase difference between the input voltage and the output voltage we are observing, because in this case this upper side will be positive and lower side will be negative, and also in the at the input side and at the output side also the upper side will be more positive than the lower side. So there will not be any phase difference. So the quantity, so we can say the increase in input will be associated with increase in output. So the voltage gain is established in this case of transistor operation. The quantity AI is slightly less than the unity, because we have seen what is AI. AI is nothing but it is IC by IE, and we have already seen that the collector current and emitter current is almost equal. Because of this equation they are almost equal, because IB is very small, a recombination lossy current part. So if IC and IB is almost equal, that means this value of current gain for a transistor amplifier is almost unity, which is the ratio between collector current and emitter current. However, RL can be made much larger than Rin. The dynamic resistance of the base emitter junction, with respect to that the load resistance can be made much larger. So if we now go back to the equation, this equation, RL if it is made much larger than Rin, then we can say that since IC and IE are almost equal, so voltage gain AV will be much dependent on RL and Rin, relation between RL and Rin, and if RL is much higher than Rin, we can say that AV will be having a considerably larger value than 1, so it will establish a sizable voltage gain by the transistor amplifier. So that's why we can say that transistor can work as an amplifier. So if we now establish the power gain of the transistor amplifier denoted by AP, how AC it is nothing but AC output power by AC input power. It is the ratio of output power and input power of the transistor amplifier, and the AC output power, the output current is IC and the input current is IE, and you know power means P equal to I square R. So IC square R means at the output side, what is R? It is the load resistance RL, and at the input side it is the IE square and Rin. Rin is the input dynamic resistance of base emitter junction. So this is the relation expression of power gain for a transistor amplifier, and from here we can write this is nothing but ICRL IE Rin. This is nothing but AV, and along with into another IC by IE, and that IC is nothing but IC by IE is nothing but AI, so it is not, written as AV into AI. So the relation between power gain, voltage gain and current gain will be AP equal to power gain equal to voltage gain AV into current gain AI. So this is the relation, basic relation of between different gains of a transistor amplifier. Okay, let us now move on to the next topic, modes of operation of transistor. Modes of operation. Depending upon the different common terminal between the input and output circuits of a transistor, now we have already come across that transistor is having one input side and another output side, and they have three different terminals. So considering combining between two input terminals, two terminals to form the input side and another two terminals to form the output side, and between them one terminal is made common to both the input and output side. Based on this, different modes of transistor operation can be established, can be shown. So depending upon the common terminal between the input and output circuits of a transistor, three modes of operations can be possible. Three modes of operation. First, let us see the common base mode or CB mode of operation. CB mode of operation. Let us draw the circuit first. This is the common base mode because this side is emitter, the base is grounded here, the bottom side is base, it is grounded, and this side is collector. The input side is selected between emitter and base. Base is common to both emitter and collector, that's why it is called common base mode. And the input circuit is between emitter and base, and the output circuit, input circuit is between EB and output circuit is between CB, or it is alternately called grounded base configuration, and it is an NPN transistor that has been selected. So this is IE as usual, this is IC, you know, this is IB, the three currents, and the voltage between E and B is VEB, plus minus. Voltage between C and B, you can connect a load resistance over here, RL, and then a supply VCC. This collector and base will give us the VCB voltage. So this is the grounded base or common base mode. That means common base means the base terminal is grounded and it is common to both the emitter and collector terminal. Between emitter and base, everything is measured for input circuit. Between collector and base, everything is measured or used for output circuit. Now the second mode is common emitter mode, CE mode. CE mode. Much like the previous one, the common emitter is common over here, so take an NPN BJT. This is the base, this side is the emitter, and this other side is the collector. So here the input should be, since base is emitter is common, that is grounded, or grounded emitter mode it is alternately called. So input circuit whatever is constituted between base and emitter BE, and output circuit is constituted between collector and emitter. So this is IB and this is VBE. Input voltage is VBE because here previously the input voltage is VEB, emitter base. Now input voltage is VBE, base emitter. It is between base and emitter, and it is an NPN BJT. Sorry, it is NPN BJT. This is IC and this is IB, the three different currents. The voltage that is being measured between collector and emitter as output voltage, it is VC. Previously it was VCB, collector and base. Here it is VCE, collector and emitter. The output voltage for the output circuit, RL, a load resistance connected with VCC. So this is the second mode of operation, or common emitter mode. The third mode of operation is common collector mode, or CC mode. Here from the name it is alternately called grounded collector mode. That means the collector is common terminal between base and emitter. So the input circuit whatever will be formed between base and collector, and the output circuit will be formed between emitter and collector, EC. So let us see the circuit diagram with an NPN BJT. So this is the NPN BJT. This side is base, this side is collector, and that is being grounded, and this side is emitter. So this is IB plus minus, this is VBC, that is this is the input voltage between base and collector, VBC. This side is this current is IC, and this current is IE. Output voltage is measured between emitter and collector, VEC, plus minus. In this case RL, a load connected to the output, with VCC, minus, plus, like this. So this is the common collector configuration, or CC mode of configuration, or grounded collector configuration of the operation of transistor amplifier. So these are three modes of operation which are very important to understand the different characteristic property and different way of working of transistor for to serve various purpose.